So good morning, folks. How are you doing? Well, I hope. So I got a solve up here for us. We have a lot of things to talk about today, so I don't want to spend too much time with it. But hopefully you've had a chance to look over these um, quadratic type. We talked a little bit at the end yesterday about factoring. That is a tool that we're going to use on this one. But the trouble with this problem and problems like this one is the fact that we have both a cosine and a sine here is disadvantageous. It would be better trying to solve this problem as a quadratic if both of the sine or both of the trig functions were the same. If we had either cosine squared and cosine or sine squared and sine, or heck, even if we had tangent squared and tangent, would be better than dealing with a sine squared and cosine squared. So it would be nice in this problem if we could do something to turn that either that sine squared into a cosine or that cosine into a sine. And of course, we do have such a tool. We do know that the cosine squared of x plus the sine squared of x is always equal to 1, which means that the sine squared of x is always equal to 1 minus the cosine squared of x. So if we take this sine squared x and replace it with 1 minus cosine squared, then this problem will be in entirely cosines, and that should make things like factoring easier for us to do. I'm going to be a little careful here and put it in parentheses. It's always a good habit when you substitute anything in to put it in parentheses when you do, in case there's a multiplication or a negative sign or something that has to distribute. But here, really, they're not doing anything. So yeah, I'm just going to strip them off. 1 minus cosine squared x minus 5 cosine x equals negative 5. And then this is a problem in which we have, a function and its square. So we really do want to approach this problem as a quadratic type problem. And for some people, when that happens, they find it a lot easier to replace the trig functions with something a little more recognizable. So I'm just going to do a little substitution here. Let u equal the cosine of x. And really what we're trying to solve is this question. It looks a little bit more like a quadratic in that form. So how do we solve quadratics? Well, we set them equal to 0. So we could have 0 equals add over the u squared, add over the 5u, subtract off the 1, we're going to get a minus 6. Once we've done that, this should be either factorable, or if not, we could certainly still use the quadratic formula. We'd have u equals the results from the quadratic formula, and then that u would go back to cosine, and the cosine would equal those quadratic formula results. It doesn't have to be factorable. Just because we're learning this, ours will just because we're learning this, ours will tend to be factorable, but they don't have to be. So we'll have u is equal to negative 6, or u is equal to 1. So when we undo that substitution and go back to our problem, we're left with, well, the u's were cosines, so we're left with cosine x equals negative 6 as one possibility, and cosine x equals 1 as the other possibility. And then we just finish off the problem by solving those. Now you could have done the factoring, the part in blue, with the cosine x's instead of the u's. Would have worked perfectly fine. Those of you going into calculus, you will find we do a lot of u substitution like that. So it's a nice habit to get into, or be okay with as a way of thinking, but you don't have to do the substitution at all. Sometimes it can help to see what your factoring looks like. But if we went to finish these off, if we tried to take the cosine inverse here, the cosine inverse of -6 is going to push out an error very quickly. And that's, of course, because the cosine never equals -6. The cosine is trapped between -1 and +1. So this is not going to generate any solutions. This thing is never equal 0 because that's -6, because the cosine can never become 6 or -6. So we're only getting our answer from that cosine x equals 1. So when we take the cosine inverse there, we're going to get a nice x equals. Where's cosine equal to 1? Cosine is equal to 1 at pi/2, at straight up, and anything coterminal to it. Now, usually for cosine, we'd have two sets of answers. That one is a positive, so usually we'd expect one answer in quadrant 1, our principal cosine inverse, and a second answer in quadrant, in quadrant 2. That's where our secondary answer would be. But as we get closer and closer to, why did I say pi/2? Pi/2 would be sine. I'm sorry. That's why you guys are looking at me funny. Actually, I can't see any of you except Shay, and Shay wasn't looking at me funny. So where is cosine equal to 1? Cosine's equal to 1 at 0 plus 2 pi k. So as we get close to 0, those two answers, one in quadrant 1 and one in quadrant 2, essentially meld together at an angle of 0. So this is one of the few exceptions where instead of getting two answers, we'll get one. You could think of it as getting that one answer twice, if that helps, but we do only get that one answer set. Anytime we're a quadrennial angle, it's a technical term. I always call them axial angles because they're on the axes, but quadrennial angles is a technical term for those angles that terminate on the axes. But anytime we have a axial angle, we're going to end up with only one solution instead of two. So that's our solution set. Questions about that? Or about solving in general? You guys have had some time to play with that. Hopefully you have been playing with that. I know the homework for it's not due until, I think, Monday, but we have a test like next week. So hopefully you're not putting this off. So with no questions, I'll move on from solving to our 7-4. But if you guys do have questions, this is a good time. I want to hear them. Going once, twice, and thrice. All right. So if something does come up, let me know in a message or on the forums or something. Do make sure you're getting good practice without solving. It does take practice to make sure you're finding those proper extra solutions. And it can be one of those things that goes very well if you have practice and very poorly if you don't. So do make sure you get that practice. Okay, I want to talk a little bit about linearity. And by linearity, I don't mean lines. I want to talk about linear operators. A linear operator is a fairly rare thing. A linear operator is something like multiplication is a linear operator. We call it a linear operator because it can be distributed among addition and subtraction. So the fact that we can take that 5 and apply that multiplying by 5 to each term of a multi-term expression and turn this into a nice 5x plus 15, that's actually a fairly rare quality of an operator. And multiplication is one of the few things that can do that. For example, if we have, say, that same x plus 3 and we were squaring it, could we say that this was equal to just x squared plus 3 squared? Is that true? Hopefully the rest of you, like Jay, are saying no. I don't know because I can't see any of you, except Dominic too. Hi, Dominic. But we certainly can't do that because squaring and powers in general are not a linear operator. We have to formally multiply this out and FOIL that out. So squaring, not linear. What about square roots? If we have the square root of, say, even something nice like x squared plus 25, can we take the square root of the x squared and then add the square root of the 25? Is that legal? Dominic's saying no. It would be nice if it was legal, except the entire world would collapse. But we can't do that. It doesn't work because radicals aren't linear. You might remember logarithms. If you had the natural log of x plus 2, was that equal to the natural log of x plus the natural log of 2? Could you distribute that natural log? Was that true? That one's a little tougher. That's not the most, alas, no. Yeah, it would be nice if we could, but no, can't do that. If they're multiplied, we can. Natural log of 2x is natural log of 2 plus natural log of x, but not when they're added. They're not linear operators. E to the x plus 2, is that e to the x plus e squared? No, we can't do just that over the addition subtraction. It's not linear. Very, very, very few things are. Functions in general, if I wanted you to find f at x plus h, given some function, like say f was, you guys remember the difference quotient? Say if f of x was x squared plus x, and we wanted to find f at x plus h, well, can we just take f of x and add it to f of h? Or do we have to plug x plus h into those? If you're following along with the theme, we have to plug the x plus h into those. We can't just break it up over adding. So linearity is fairly rare. Now, for those of you who are going to go on to calculus, your differentiation and integration in calculus, your two primary tools in calculus 1 and 2, are linear. We do get to use them term by term, and it's super, super handy that we get to do that. But it's very rare that we get to do that. Now, why am I talking about that? Well, because we are going to start having more going on within our trig functions. So we're going to be looking at things like the cosine of, let's say pi over 4 minus pi over 6. And wanting to be able to figure out what that is exactly. Or if those were of variables, being able to break them up. Just being able to manipulate that. And one might want it to be cosine pi over 4 minus the cosine of pi over 6, because that would be nice. but that wasn't true for functions in general. It wasn't true for exponents. It wasn't true for logarithms. It wasn't true for radicals. It wasn't true for powers. The only thing it's been true for in most of your mathematical careers is multiplication. Is this multiplication? Then you can't distribute. Cosine, sine, tangent, cotangent, cosecant, secant are not linear operators. So this doesn't work. It's not true, and it will never be true. Well, there's probably specific cases that you could make it work, but. And if we wanted to test that that's not true, we could figure out what the cosine of pi over 4 minus the cosine of pi over 6 is. We know those values. It's the square root of 2 over 2 minus the square root of 3 over 2. We could subtract those and get a value. And frankly, that value would be negative, right? Value would be something negative. Well, cosine of pi over 4 minus pi over 6, pi over 4 minus pi over 6, if we did the math, is pi over 12. Pi over 12 is right there, and the cosine of pi over 12 is not negative. This would be negative. So already we know it doesn't work. So no, we can't do that. So just like, well, what do we do when we square stuff, and what do we do? We need to have an alternative. We need to know, okay, what can we do? What kind of manipulation power will we have in situations like this, especially when these aren't numbers, when they're X's and B's and A's and all kinds of fun stuff. So that's what we want to explore today. What manipulation power do we have? Do we have any nice tools that are going to allow us to find these nicely? I did not mean to get rid of my circle. Ooh, a pink circle, that'll be fun. I don't know why, but it seems like that should be fun. Okay. So first off, we're going to do this in general. So instead of specific values, I'm going to have an angle A and an angle B and look at their difference. So to do that, I need some angles. So I'm going to draw us an angle A. I'm putting it in quadrant 2 for no particular reason. Makes the diagram look nice, but doesn't have to be in quadrant 2. And angle B, I'm going to draw there. So I've got angle A and angle B. Again, they don't have to be in quadrants 2 and 1. Frankly, A doesn't even have to be bigger than B. It just makes the diagram look nice. So that's our two angles in there. And we want to figure out a way we can express this in terms of A and B separately. So I want to compare this diagram with angle A and angle B in it to a different but same scale circle. Oops. Doesn't have to be precise, but it's nice if it's nice. With this angle A minus B in it. So the angle A minus B is going to be that angle. So I'm going to take that angle and put it in standard position. So this angle here is this angle A minus B. So for example, if A was 100 degrees and B was 50 degrees, I don't want 50, say it was 60 degrees, then the A minus B would be 40 degrees, so this would be a 40-degree angle in standard position. Fair? So this blue angle and that blue angle are the same. Now, the key to making the tool that we're going to make is an observation that if this circle doesn't even matter what the radius of the circle is, as long as they're the same radius. We're going to work under the presumption that it is a circle of radius 1. If it isn't, we can always make a smaller circle in there that does have radius 1 and do this. So I want to look at this distance between those two intercepts. And the idea is that that distance has to be the same as the distance here. This distance, I'm going to call D2, has to equal that distance D1. Essentially, you can imagine that it's just that black, green, purple triangle rotated down to make the black, blue, green triangle. It's the same triangle, it's just rotated. Does that seem reasonable? My diagram's not quite to scale, but does it seem reasonable that if these angles are all matching up, that those two lengths have to be the same length? I want to make sure you guys are happy with that, because it is the basis of the entire argument. Good, you guys seem happy with that. So if those two are supposed to be equal, and I want to build a link between A minus B and the angles A and B separately, that distance is going to provide our link. So we need an argument for distance. And you may remember we do have a formula for distance. It is often referred to as the distance formula, just to be cryptic. But good old square root of x2 minus x1 squared plus y2 minus y1 squared, all that thing's square root. I'm not a big fan of this formula, mostly because this formula is just Pythagorean theorem. It's change in the x's plus the square of the change in the y's should be the square of the distance. Yeah, we know the square of this plus the square of that should be the square of the distance. That's Pythagorean theorem. All the distance formula does is square root both sides, so it's always positive. So, you know, are we using distance formula or are we using the Pythagorean theorem? It's the same thing, so it doesn't matter. But we'll start this problem at least in distance formula form. So if we want to write out this distance, we would need these coordinates. The nice thing is we know these coordinates. This coordinate on angle A, its x value is the cosine of A. That's our definition of cosine. The cosine is the x value of where it intersects with the unit circle. The y value is the sine of A. If we know the angle A, we know those trig values. This other point, the point on angle B, well, its x value is going to be the cosine of B. Its y value is going to be the sine of B. Again, if we know the angles A and B, we can find those points. So what's the distance 1 going to be? Well, it's going to be the square root of the change in our x's. So I'm going to go A to B. So it's going to be the cosine of A minus the cosine of B, quantity squared, plus the sine of A minus the sine of B, quantity squared. That's just distance formula between those 2 points. We put in angle A, angle B, that'll crank out that distance. Then we're going to do the same thing down here. So again, this point down here for angle A minus B, its x value is the cosine of A minus B. Its y value is the sine of A minus B. And we want to find the distance between that point and this point. Now, it might seem like we don't have an angle for that point, but the nice thing is we know the coordinates of this point. The coordinates of that point are 1, 0. So that's actually really nice. So that's going to equal the square root of the change in our x's again. So cosine of A minus B minus 1 squared plus the sine of a minus b, the difference in our y's, the sine of a minus b minus 0 squared. Now, we're certainly not going to stop there, but our goal was to build a relationship between the cosine of a minus b and the cosines and or sines of a and b individually. So this is going to be what's going to link those two things, and it's already essentially doing that. The right side is an argument in terms of the sine and cosine of a minus b. The left side is the cosines and sines of a and b separately. So this is going to build us towards an argument that will allow us to rewrite this cosine of a minus b as some expression in terms of sine and cosine of a and b separately. And that's the goal of this tool. But we don't want the tool to look like this. We'd love to have it preferably solved for cosine of a minus b, but certainly cleaned up quite a bit. Now, usually I try to make people kind of go through some of this on their own. I'd love to just kind of say, hey, simplify this and kind of check up on you as you do it. But unfortunately, I can only watch a couple of you, and that might take a little bit more time in this format. But I do encourage you to go through these calculations later on your own. But I do want to kind of go through them together, at least quickly, so we have a sense of where this tool is coming from. Because this one argument is going to build like 12 different tools for us coming from this one construction. So it is a fairly pivotal construction in trigonometric identities. But the first thing we're going to do is get rid of these square roots. Because if the square root of all that stuff, all that junk, is equal to the square root of this other junk, if you have the square root of m is equal to the square root of n, if the square roots are equal, the arguments have to be equal. The square roots are only equal if those things are equal. So we actually don't even need those big square roots there. Yeah, they're part of our definition. If we were actually caring what that distance was, we'd need the square roots, but all we're trying to say is that they're equal. So the square of them is also equal. So that's a nice first thing to do, is just get rid of those square roots. It's actually surprisingly common when you can just throw square roots away because you're trying to build equality. And then I'm going to write this as sine squared a minus b. So even just that is nice. Now, many of you are probably thinking, gosh, I hope we don't have to FOIL this out. But we certainly know that this cosine a minus cosine b quantity squared is not the cosine squared of a minus the cosine squared of b. The whole point of this is linearity doesn't happen. So we can't just square those pieces. We do need to FOIL this out, and we need to FOIL this out, and we even need to FOIL that out. So this next line is a lot, but nice stuff starts to happen. So let's just multiply these out and see what happens. We have cosine squared a minus 2 times the cosine of a times the cosine of b plus the cosine squared of b. That's the square of this first one. You might have seen the pattern before. Square of the first, twice the product, square of the last. That's all I'm using. Plus, FOIL that thing out. Same thing. Square of the first, twice the product between them. So twice sine A, sine B, plus the square of the last, sine squared B, equals. Well, we've already gone this far. Why don't we go ahead and just write this whole line out? It is nice that we get to square trig functions, isn't it? So let's go ahead and multiply this side out. I'm going to keep it dark green just to kind of keep track of them. We're going to have cosine squared a minus b minus 2 times their product, so cosine a minus b, sorry, this is getting squished, times 1, but the times 1 we don't need, plus the 1 squared is 1, and then I'm going to write the plus sine squared a minus b down here. And actually, I'm going to get rid of that circle so it's just not in the way, and rewrite that. So that plus sine squared a minus b. Okay, so as long as I didn't do anything silly there, that's our big line. Foiled everything out. And I suggested some nice things were going to happen. Let's look at those nice things. Felix mentioned how convenient it was that we're getting squared trig functions. We like squared trig functions. We have a lot of control over squared trig functions. Specifically, what do we know about the cosine squared of a plus the sine squared of a? What's cosine squared a plus sine squared a? It's 1. Well, what about cosine squared b plus sine squared b? That's also 1. So those immediately go away. Okay, we're stuck with the minus 2 cosine a cosine b and the minus 2 sine a sine b. But that's okay. We got rid of some big, huge chunks there. On the other side, well, if we look at the other side, yeah, it's cosine squared a minus b and a sine 1, 2. I get you. There's a cosine squared of a minus b plus a sine squared of a minus b. So again, that's a 1. Plus, well, there already was a 1 over there, so it's got another 1 over there. Minus 2 cosine a minus b. So that's nice. A lot happened with those relationships. We can collect some like terms here. That's going to be 2 minus 2 cosine a cosine b. I guess I'm switching to one color now. Minus 2 sine a sine b equals 2 minus 2 cosine a minus b. We could certainly subtract 2 from both sides, and those would go away. I'm also going to divide both sides by negative 2. And we're going to be left with a very nice, I divided the 2, sorry. A very nice cosine A times cosine B divided by that negative 2, so it's becoming a plus sine A sine B being equal to, divided off the negative 2, so that's equal to our cosine A minus B. That's what we wanted. We wanted an expression for cosine of A minus B. What can we do to open up cosine of A minus B? And this is that relationship. So now, if somebody comes along and says, hey, I want to know what the cosine of pi over 4 minus pi over 6 is exactly, well, we know it's not cosine pi over 4 minus cosine of pi over 6 because that was negative instead of positive, and it's not a linear operator, so we know we can't do that. What can we do? Well, we can turn this into the cosine of A, cosine of the first one, cosine of pi over 6, sorry, pi over 4, times the cosine of the second one, pi over 6, plus the sine of pi over 4 times the sine of pi over 6. Those two expressions are equal. because the length of that bar was equal in both cases. And the nice thing is each of those we know. We know what the cosine of pi over 4 is. It's the square root of 2 over 2. We know what the cosine of pi over 6 is. It's the square root of 3 over 2. Plus, we know what the cosine of pi over 4 is. It's another square root of 2 over 2. We know what the sine of pi over 6 is. That's a 1/2. So how about square root of 6 over 4 plus square root of 2 over 4? So this thing equals the square root of 6 plus the square root of 2 all over 4. We have to go through this whole process for all 6 other trig functions. Well, we also have to go through this process for cosine of a plus b, and then all the other trig functions. So it's not like we'd have 5 more, we'd have 11 more. But remember how I said this construction actually builds us 12 relationships? We actually get the other trig functions and the pluses instead of the minuses in a much quicker argument once we know this. So as long as we're comfortable with this tool, we'll be able to do a lot more. So before we talk about the other trig functions, though, I know we went through this construction fairly fast. If you were asked, prove this, this is what the proof would look like. No one's going to ask you to do that, unfortunately. Unless you become a math teacher, it's a great life, so I do recommend it. But unless you're going to do that, no one's going to probably ask you to prove this. But does it make sense where all these manipulations are coming from to build this relationship? Because at the end of the day, what we're really looking at is just this relationship. If we are faced with the cosine of a difference, we can break it up into the product of the cosine values plus, notice the sign switches, plus the product of the sine functions. Also, by the way, this works the other direction. If somebody wanted us to solve, say, the cosine of theta times the cosine of 0.3 plus the sine of theta times the sine of 0.3. That might seem like, well, when's that going to happen that those match? It actually happens a lot because you're looking at the horizontal and vertical components of, say, like a force. So it's very common for those angles to match that way. Trying to solve this with the two statements here is really irritating. But if we can use this tool to bring this together, so we have the cosine of theta minus 0.3, and we want to set that equal to something, I don't know, 1/2, set that equal to 1/2. We can now solve this. Take the cosine inverse of both sides, add over that 0.3, remember about your coterminals and your second answer set. So this isn't just a way to find exact values for things. This is a common set of manipulation tools that we will use, especially you guys going into calculus and physics, especially physics. But Felix, you're absolutely right. Having to go through an argument, it's not a bad argument. It's actually kind of a cool argument. But trying to go through that argument for all of the other relationships would be time consuming and kind of easy to get lost in. But again, the best part is we don't have to. If we want, say, the cosine of a plus b instead, well, we know the cosine of a plus b. If I'm allowed to go off to the side here, we know the cosine of a plus b is the same as the cosine of a minus the opposite of b. That's the same as the cosine of a plus b. Well, and we have a tool for subtraction. Okay, so it's just going to be the cosine of a times the cosine of the opposite of b plus the sine of a times the sine of the opposite of b. But even better, if we remember that the cosine is an even function, the cosine of the opposite of something, changing from negatives to positives, doesn't change the answer for cosine. If you remember, cosine is even, right? So it's the same on both sides. So whatever happens at B is the same thing as what happens at the opposite of B. So this just turns into the cosine of A times the cosine of B. That's going to be the sine of A. And again, remember, sine is an even function. Whatever happens at B is the opposite of what happens at the sine of the opposite of B. So this sine of the opposite of B becomes negative sine B. So I'm going to pull that negative all the way out. Sine B. So we don't need to go through an entire construction like that. Just using our even and odd identities, we get the cosine of A times the cosine of B. Again, that negative just goes away in the cosine, but the negative on the B in the sine flips the sign. So it's almost entirely the same relationship. The only thing that changed is the positive to the negative. So we get that without having to do too much more work. You're not even often going to see it written that way. You'll often see it written as the cosine of A plus or minus B equals the cosine of A minus plus sine A sine B. Notice here it's plus or minus. Here it's minus plus. The top one goes with the top one. The bottom one goes with the bottom one. You'll see that notation a fair amount. So just so you know what that means, if they switch the orientation of the plus and minus, that means they oscillate. So we didn't have to go through a lot to build the subtraction tool or the addition tool on top of our subtraction tool. But that really wasn't what you were talking about, Felix, was it? You were talking about the other trig function. So what about sine? So let's say we want to build the sine of either A plus or minus B. Doesn't matter which. Let's go ahead and do the minus one first. We'll build the plus one in almost the same way we did this one. So let's look. How would we do that? Sine of A minus B. Well, I don't know a tool for sine for this. All we know is tools for cosine. So wouldn't it be nice to change this sine into a cosine? Yes, it would be. It would be easy if it was a sine squared. It's not. Maybe we could put in a sine squared and a square root, but that's messy. It's actually a lot easier to turn this into the cosine of pi over 2 minus A minus B. You might remember back to our cofunction identities, the cosine of 90 degrees minus theta was equal to the sine of theta. You switched from an angle to its complement. You switched from a function to its cofunction. So I am reaching back a bit to get that function, but it allows us to turn the sine argument into a cosine argument. And we have cosine arguments for addition and subtraction. I do want to manipulate this a little bit first. Cosine of pi over 2 minus A, distribute that negative, plus B. So I can look at this as cosine of this plus that, and use our cosine tool for adding. Cosine tool for adding would say this is the cosine of pi over 2 minus A times the cosine of B minus, remember the plus turns into a minus, the sine of pi over 2 minus A times the, times the sine of B. But we're almost done here. But the cosine of pi over 2 minus A, that's the same as the sine of A by our cofunction identities, times the cosine of B minus sine of pi over 2 minus A, that's the cosine of A, times the sine of b. So with just a little manipulation, okay, it's a fair amount of manipulation, but it's just careful uses of our cofunction identities. We can turn this into, instead of the cosine A cosine B, it's the sine A cosine B. And notice this minus stayed a minus, so it's going to be minus sine B cosine A. And you could have put cosine A sine B. I just like the sine first for some reason, but either order is fine. A similar argument about even and odd functions will give us that the plus stays a plus, because the only ones that are going to be negative are the handy ones. So we could go through that argument too, but you guys are going to get sick of hearing these arguments pretty quickly. But just little tossing around, those manipulations that we've been practicing in 7.2 and 7.1, being able to manipulate these things to make new arguments are going to build us these tools much faster than going through a big construction like this every time. Before we're done, it might be nice to have tangent. What we'll do tomorrow is play with these tools a lot. I wanted to get through today having these tools at our disposal, so tomorrow we could play with them. But we still certainly do need to make tangent of A plus or minus B. But any guesses on how we're going to make tangent? What's a nice relationship you know about tangent? There's been way too much of me talking. Felix, yeah, sine over cosine. Having arguments there is nice, but shorthanding in the chat, I'll let that go. Tangent of A plus or minus B is going to be the sine of A plus or minus B over the cosine of A plus or minus B. And yeah, we're going to build both the plus and the minus at the same time here. We know what the sine looks like, the sine of A plus or minus B. That's the formula we just built. So that's going to be the sine of A cosine of B plus or minus the sine of B cosine of A over cosine of A plus or minus B. That's the first tool we built. So that's going to be the cosine of A cosine of B minus plus. Remember, on cosine, the sign switches. Sine of A, sine of B. And frankly, we could stop there and say, hey, that's our tangent tool. But it's actually a really handy manipulation. If we multiply the top of this by 1 over the cosine of A cosine of B, and the bottom of this by the same, of course they have to be the same, cosine of A cosine of B, something really nice happens. Here, let me do it that way. Here, the cosine B is going to cancel with that cosine B, leaving us with sine A over cosine A. Well, sine A over cosine A is the tangent of A. Fair? Oops. Over here, the cosine of A cancels with this cosine of A, leaving us sine B over cosine B. So that's going to be plus tangent of B. Cosine A cosine B over cosine A cosine B is 1. That is plus or minus up there still. So 1 minus plus minus plus. Sine A over cosine A gives us tangent A. Sine B over cosine B gives us tangent B. So usually that's how we see the tangent relationship. Tangent of A plus or minus the tangent of B, all over 1 minus plus. Again, The sign switches on the bottom because of cosine. Tangent A, tangent B. So we get all of those relationships. There's really 6 relationships there from this one construction. We could technically build a secant, cosecant, and cotangent relationship, but we don't tend to. We turn everything into sine, cosine, and tangent to be able to build it. So we still do have 6 more relationships coming down the pipe from this tool, but we'll build those later. So this one argument so far has built us these 3 tools, well, plus and minus, so 6 tools, with just some of our identity manipulation. So now if somebody was to come up to you, I know you guys got to go, but if somebody comes up to you and says, hey, I want to know exactly what is the tangent of 5 pi over 12, and one person tells them, well, I don't know over 12s. Our exact angles only deal with pi over 6s, pi over 4s, and pi over 3s. So we can't do it. You're going to go, no, 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 we can do it. As long as we can come up with 2 things that we can add or subtract to make 5 pi over 12 that we do know, will be good. So let's say, how about 8 pi over 12 minus 3 pi over 12? That's 5 pi over 12, right? I'm going to assume you all said yes. 8 minus 3 is 5. Well, 8 pi over 12 can reduce to, what, 2 pi over 3 minus pi over 4? We know about 2 pi over 3s and pi over 4s. So that's going to be the tangent of 2 pi over 3 minus the tangent of pi over 4 over 1 plus the tangent of 2 pi over 3 times the tangent of pi over 4. We know each one of those values. We can plug them in. Do you want to do that before you go? I was going to end the argument there and just say, figure that out and you have a value, but might as well figure it out before we go. 2 pi over 3 is over here. So our coordinates would be, what, the negative 1/2 and square root of 3 over 2. So tangent is sine over cosine. So it's going to be negative square root of 3 minus 1 over 1 plus the opposite of the square root of 3 times 1. So negative square root of 3 minus 1 over 1 minus the square root of 3. Or better yet, how about square root of 3 plus 1 over the square root of 3 minus 1 to distribute the sign down there so it's cleaner. And that's an exact value for the tangent of 5 pi over 12. You could rationalize the denominator if you really wanted to, but I don't think you're going to help anybody by doing it. You might. I don't care, though, right now. You guys got to go. So this is the beginning of some of those old-fashioned tools when we didn't have calculators and we had to build every angle from angles we knew. So you would take these and then use them to build other angles and take those other angles to build more angles and so on and so on and so on. We're not going to use it so much for that. We're going to use it for algebraic style manipulation. But this is a really big tool that we're going to use. I will remember next time some guy comes up and asks the exact value. Hopefully you don't necessarily remember square root of 3 plus 1 over square root of 3 minus 1, but hopefully you'll remember the technique, Felix. That is why we are here. So tomorrow we'll go through a bunch of things that we're going to do with this stuff, but this is certainly one of them. Being asked for, find the exact value of 5 pi over 12, or find the cosine of negative 7 pi over 12, or we'll have some over 8s and some different ones. We're not going to go too crazy. They're all going to be 1 or 2 step problems, but you can do this with, nasty radian measures, as long as you can find some combination of some finite number of fractions we know to build the fraction we want. You can do it. It can take hours. Again, we're not going to do that. We're going to use it for algebraic manipulation, but it's a good way to practice this tool on a small scale. Questions about that before you guys head off today? I know today was a lot of building. This is always both kind of a fun day for me because I get to derive a whole bunch of formulas, but kind of a eye glaze over day for you guys because it's a lot of manipulation thrown at you all at once. So tomorrow will be more you guys working examples of how we're going to use these tools. So come tomorrow ready to communicate. So that's all I got. Have a wonderful day. We did have a math department meeting yesterday, and we did discuss whether or not we should assign like 5% of the grade to people who turn their cameras on. I actually voted that that would be an unfair thing for us to do, but gosh, I like the idea. Somebody said, well, maybe extra credit. I was like, it still seems unfair, but it's more fair. That's the nice thing about extra credit. Extra credit can be unfair. Yes, you do. You lose it because you don't have 5%. You'll make it up somewhere. I'm not worried. So come tomorrow ready to be more involved because you're going to be doing a lot of calculations and a lot of work tomorrow. Not a lot of work, just a lot of, be doing stuff on your own, less passive. All right, that's all for me. If you guys need anything, send me a message.